In a Field Programmable Gate Array, or FPGA, the labs are all arranged into a large array, and the device can be programmed and reprogrammed out in the field. Programmable routing is placed in the spaces between labs, similar to streets in a large city. This routing is organized as row or column in the interconnect. It may span the entire length or width of the device, or only a small segment, covering only a few labs in a row or column. Various device blocks, as well as other routing resources, can all drive into a given routing resource. This makes it very flexible for FPGAs to route various signals around the chip. The routing channels in FPGA devices seem simple, but they actually provide lots of functionality and connectivity. FPGA routing channels allow all device resources to communicate with all other resources anywhere on the chip. This was not always the case in some older non-FPGA devices. The Manhattan-type routing channels, along with different-sized fixed-length segments, make it easier to adjust routing to meet design timing requirements. As already mentioned, as the amount of available device resources grows, the number of routing channels only needs to increase linearly to continue to connect between all device resources. FPGA routing channels can be divided into two types: local interconnect and row and column interconnect. Local interconnect routes directly between LEs or ALMs within a single lab, while providing shortcuts, often referred to as direct links, between adjacent labs. This is almost analogous to the programmable arrays found in CPLD labs. But FPGA local interconnect is separate from the lab logic it serves. The other types of interconnect is the row and column interconnect. This interconnect comes in fixed lengths and spans either a select number of labs or the entire length or width of the device. Lab I/O can connect to the local interconnect for high-speed local operation, or directly to the row and column interconnect to transfer data to other parts of the chip. FPGA I/O control is contained in blocks found around the outer edge of the array and made available to all device resources through the FPGA routing channels. I/O blocks in FPGA devices are usually referred to as I/O elements. I/O elements contain most of the same basic features found in the older CPLD I/O control blocks, but they add many more features, making FPGA I/O elements extremely versatile for all types of designs. Besides basic input, output, and bidirectional signaling, I/O pins support a wide variety of I/O standards, including many of the latest low-voltage, high-speed standards. Pairs of I/O pins can be combined to support differential signaling I/O standards, such as LVDS. Other features include variable current drive strength and slew rate control to help improve board-level signal integrity. On-chip termination in the form of pull-up resistors can be enabled to help reduce termination component usage on the board. Some devices include clamping diodes in I/O elements that can be enabled when used as I/O for PCI bus. Any unused I/O pins on the device can be set to open drain or tri-stated depending on the needs of the design. These are just examples of the capabilities of a typical I/O element. Some devices may provide even more features. Here is what the basic logic of a typical I/O element looks like. Not shown in this diagram is all the other hardware used to control many of the aforementioned features of the I/O element. The I/O element is divided into three major sections. The input path captures incoming data on input pins in an input register, or connects the input directly to logic in the device through the routing channels. The output path contains output registers for synchronizing logic or for memory usage, similar to the output register found in CPLD macro cells. Since registers are found in both the main lab logic as well as in the I/O element, either can be used, freeing up registers in logic for other use. Of course, the register in the I/O element can be bypassed if desired. The final section of the I/O element is the output enable logic. This logic controls the output enable buffer. This section may be used if the I/O has been configured as bidirectional pin or to synchronize output data with other outputs on the device. Modern FPGA devices contain specialized hardware blocks in addition to labs. These dedicated resource blocks take up one or more blocks in the array and are completely accessible through the FPGA routing channels. Often these specialized resources are arranged in a particular row or column of the blocks in the device. Memory blocks are dedicated blocks that can be configured into different types of memory devices. FPGA memory blocks can be constructed into single or dual port RAM or programmed ROMs. They can also be used as shift registers or FIFO buffers in place of lab logic. Since FPGA memory blocks are programmed just like other structures in the device, they can be initialized with any memory content desired at power-up. This is extremely useful for this design debugging since any memory pattern can be initialized and tested. Some devices include memory labs or MLabs. An MLab can be used as standard lab, but it can also be configured as a simple dual-port SRAM. The capacity of an MLab is much smaller than a dedicated memory block, but has a wide and shallow memory. It can implement the shifting and FIFO operations required for DSP applications without wasting a high-capacity memory block resource. The other type of dedicated resource block typically found in modern FPGA devices is called a DSP block. The DSP block contains embedded multipliers and adders to perform arithmetic and multiply-accumulate operations. They can be used instead of ALM logic to improve arithmetic performance in a design. A portion of a block diagram for a DSP block is shown on this particular slide. Some devices also feature high-speed transceivers. These I/O structures support high-speed protocols with transfer rates in the gigabit per second or higher range. These high transfer rates are typically used for communication networking devices. Altera devices support dozens of I/O standards used in a variety of different applications. Different FPGA devices contain different amounts of these type of specialized resources. The device handbook should always be consulted to determine if a particular device provides enough resources for a given design. Since FPGAs are based on synchronized register logic, clocking and clock control structures are an important part of an FPGA architecture. Clocks are basically high fan-out control signals, so FPGA devices include hardware to control where the clock signals should go and how the clock signals get to their destination. All FPGA devices include dedicated clock input pins. These pins take in a clock signal and connect it directly to other clock control structures on the chip. Other pins can be used as clock pins, but the signal may need to go through other logic structures. When not used for clocking, clock input pins can be used as standard I/O. Clock input pins typically feed into phase lock loops, or PLLs, on the device. PLLs can generate other clock domains based on the characteristics of the input clock and ensure that all clock domains are in phase with each other with minimal skew. We'll look at PLLs in more detail in a moment. Advanced FPGAs also include delay lock loops, or DLLs. DLLs are useful for adjusting and locking the phase of a clock quickly. They are mostly used along with PLLs when creating an external memory interface, such as one that controls external DDR3 SDRAM memory. The DLL dynamically adjusts the phase of a strobe signal to align it correctly with the data being read and clocked by the strobe. The addition of a DLL into such a design provides much more accurate tracking when changes in voltage and temperatures are detected, allowing for some devices to achieve much greater memory interface speeds. Clock control blocks are basically clock control traffic cobs. They are used to select which available clock should feed the device's clock routing network. They are also used to enable or disable selected clocks during power up or power down. The ability to enable or disable selected clock is also a device power saving technique. Any logic normally clocked by a clock that gets disabled is essentially shut down, saving overall dynamic power. The clock routing network consists of a routing channel used to fan out clocks to all the logic in the device. These are special routing channels that are usually separate from regular row and column interconnects. The global network of clock interconnect may connect to all logic, but some devices contain regional or hierarchical clock networks that feed only certain parts of the device. For example, a clock network may feed only a single quadrant of the device. In this way, a clock used for a particular region or part of the device does not use up the global clock routing network, saving clock resources. As